And welcome to Module 5, Lesson 4, Calculating Probability for Chance Experiments with Equally Likely Outcomes. Okay, again, this is the second go-round for this one, and yeah, with no further ado, let's move into something called theoretical probability. Okay, theoretical probability. We'll talk a bit more about that later, what it means, and we're going to do an interesting little experiment right here that may or may not prove anything about theoretical probability. So, here's what we're going to do. And again, here is our in order to estimate the probability of an event for a chance experiment, you divide. Okay, and what you divide is the number of observed occurrences of an event, and then the total number of observations. So as you can see, for this experiment, there are going to be 20 trials, okay, or 20 observations. Okay, so that is going to be our denominator, 20. Okay, all right, and then of course our number of observed occurrences of the event, that will vary from, in this case, color to color. It may or may not vary. In truth, if it were, I won't get into it. I won't tell you too much. Okay, but anyway, I have, and I actually did this already. I had found a small paper bag, and inside of it I put some cubes. Okay, and the cubes were identical except for their color. Okay, now that is a very important point, and very important in science. This idea of we control all the other variables. The only thing that is different about these cubes are their colors. Okay, are their colors, and I mean, again, that's very important. These are all that color is called a variable, and that is what we call our independent variable. Okay, it is the one we will could be different. Okay. So, but as far as their size, they're the same size. They are 1 centimeter by 1 centimeter by 1 centimeter cubed. Okay, a centimeter cubed. These small little centimeter cubes you probably used before. Again, really important that they're all the same, because when I stick my hand in, or when I stuck my hand in there to the bag to grab them, I mean, I could feel no difference in the cube because it was the same exact size and shape. Okay, and I guess the cube would be the same shape as another cube. Anyway, yeah, so your teacher, that's me, will conduct a chance experiment by randomly drawing a cube with replacement from the bag. Record the outcome of each draw in the table below. Okay, important point here. More important stuff, yeah. And that is, we will be replacing picked cubes so that there are always the same number of cubes in the bag. Okay, this idea of replacement, and the way we state it statistically usually is with replacement. Okay, that means I put my hand in there and I pick out a red cube. I am not going to keep it out, because if I did keep it out of the bag, what would that do to my chances of picking a red cube? That's right, okay, it would go down, all right? If I do have various colored cubes in that bag, and I had only a certain number of red, my chances of pulling out that red one are going to be diminished if I don't put it back in, okay? So in this case, we're going to keep replacing. Every single time we're going to have the same number of cubes, and the exact same cubes in that bag at any given time. Okay, so here we go. I did this, okay, and these are my results. Okay, you can see my results here. Pretty heavy on the yellow. Honestly, you would swear early on in my trials here. Look at this: yellow, 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 yellow. There were 4 out of 5 yellows. Had we stopped the experiment at that point, what might you have believed was in the bag? You probably and justifiably would have thought that there were a bunch of yellows or more yellows in the bag. I'm not going to tell you if that is or is not the case, but at that point you might have been inclined to believe so. Okay. Okay, and as I did that trial, I wanted to go ahead. I decided to do a different trial, second trial. Okay, again, because this is all about chance. I wasn't expecting my results to be the same, of course, but I just wanted to see how things went. Okay, and then I did, and my results were a bit different. Okay, even though my yellow did again dominate. I'm not sure what was going on with those yellow cubes today for me. The results were a little bit different. So let me go show you here what happened. So in my first trial, I had 10 yellow, 5 blue, 4 green, and then 1 red only. Okay, my first trial, my first experiment, that's what I pulled out of the bag. Okay, and you can see very, very heavy on the yellow. My second trial, okay, I had 7 yellow, 5 blue, 3 green, and 5 red. So now what we might have been guessing about the contents of the bag after my first trial might be switched or adjusted based on the results of my second trial. Okay, as you see, those are quite different, with the exception of the blue, which was 5 both times. Now again, you don't know how many cubes I have in this bag yet, okay, or how many of each color. I think you get the sense that there are 4 colors in that bag. Could there be a 5th color? Absolutely. Could be one of purple or something in there. It could very well be. But we'll move on here. All right. So now, based on the 20 trials, and again, you don't have any information about how many cubes are in that bag. You don't know exactly how many colors are in that bag. You may be getting an idea of both of those things. But based on the 20 trials, estimate the probability of choosing a yellow cube. Okay? And now choosing a yellow cube, and again, based on those 20 trials, now I decided to go ahead and, for my trials, I went ahead and used the second batch. Okay? And my yellow turned out to be a 7 out of 20, or 35% probability. Okay, they've been working. Actually, most of this lesson will work with fractions. Okay, so that fraction representation of 7 over 20 probably more important. But one thing I wanted to do here, I just wanted to point something out. If you notice, when you have 20 as your denominator, very interesting and very really a lot easier. If you notice something here, if you have 20, and now to get to 100 from 20, you would multiply by 5. Okay, so whenever you have 20ths, 20 in your denominator, all you have to do is multiply your numerator by 5, and of course 7 times 5 is 35. So I always know what my percentage is with 20. It's very easy. I'm just going to multiply my numerator by 5, and I got my percent there. Okay, just an interesting thing I think some of you knew already, but yeah, you can never know enough, right? That's for sure nowadays. All right, now choosing a green cube. Okay, what is the probability of and again, these are all estimates of based on that trial, and that was 3 out of 20, or 15%. And you can see that 3 times 5 is 15, so 15%, or 3 out of 20. Red cube was 5 out of 20, or 25%. And a blue cube, the same, 5 out of 20 or 25%. Now, all of these probabilities are all based on that second trial. Okay. Now, this question here, number 2, asks if there are 40 cubes in the bag. And again, if there are 40 cubes in the bag, how many cubes of each color are in the bag? Okay. Now, how many cubes of each color would you predict are in the bag, or based on these trials? Okay, based on these trials. So go ahead and pause and do that, and come on back. Okay, well, based on these trials, you might look at it this way. Okay, so how many cubes are in the bag? Now, 10. All right, 10 times 4 is 40. Okay, so 10 times 4 is 40. I'm not sure what I did there. Hold on a second. I must have missed making those strokes at the beginning. When I put this together. Anyway, yeah. So if we go ahead and do this, we're based on these trials up here. Okay. So if we take yellow, for example, let's start up here with yellow. Okay, and we had 7 out of 20, or 7/20ths were yellow. Okay. Now remember, we had 35% of our picks were yellow. Therefore, 37. So 77/20ths of 40, because we're trying to figure out of 40. Okay, that is the same as saying, remember this is 7/20ths times 40 over 1. Okay, and then if we go ahead and work this out, and again, so then we would have 14. Okay, all right, and hopefully that didn't confuse all of you or any of you, because we've done this quite a bit before, and hopefully this is something you're feeling very proficient with. So, based on our results, again, based on our 20 trials, if we were to have if there were 40 cubes in that bag, we would predict, okay, or we would estimate that there were 14 yellow. Okay, so let's go ahead and take a look at another color. Actually, we only need to do this 2 more times because we only have 2 more fractions. All right. So if we look at green, green was 3/20ths. Okay, and if we multiply that by 40, because this is the number we're saying are in there. Okay, we are looking at 6. Okay, so 6 green. This is our estimate for green. Okay, and then just one more time, because both blue and red were the same, and blue and red were both 5/20, which is also 1/4. We multiply that by 40. Okay, we get 10. All right, so we have 10. We would say 10 red, and then 10 blue. And again, these are all of our estimates. I know I've said this 100,000 times, but all of these are estimates based on our 20 trials. Okay, 20 trials. We do not know that these are correct yet. Okay. All right, so down at the bottom there it says, if your teacher, were to randomly draw another 20 cubes, one at a time and with replacement for the bag, would you see exactly the same results? Explain, and why? Well, you'd have to know that answer would be no, and of course we have actually seen that based on, I have already done 2 trials. Okay, I did 2 trials. You saw how different those were. I had chosen 10 yellow that first time, and second time I chose 7. Yeah, so no, it won't be the same, and it probably never be the same, and if it was the same, it's just chance. Okay, just absolute chance. Okay, and yeah, chance and randomness, lots of randomness involved. Okay. All right, so we are going to find the fraction of each color of the cubes in the bag. But first, let me go ahead and give you a bit of information. There were indeed 10 cubes of each color in the bag. There were 10 blue, 10 red, 10 green, and 10 yellow. And I wonder if that surprises you. Okay, because based on the results of my 2 trials, you could safely assume, and again, it's never safe to assume. Probably shouldn't use those 2 words together, but you may indeed, justifiably predict that there were more than 10 yellow, because I picked such a large number of yellow. I actually picked 10 yellow the first time around, out of 20 picks. Okay, but the others you may not have thought to be in equal equal numbers. Okay, and again, I could do this again, and I would get entirely different numbers. All right. So let's go ahead and use that information to go ahead and come up with our probability for each of these colors to be picked. And in fact, we make a fraction of each of the colors in the bag. Each of the colors in the bag equal 10 over 40, because there's 10 of each color out of a total of 40. Okay, and that, of course, is 1 over 4, or 1/4. Okay, so each of the 4 colors has a fraction probability, or fractional probability, of 1/4, or 1 out of 4. Okay, now each fraction is the theoretical probability. Again, very, very important that we distinguish this idea of theoretical probability of choosing a particular color of cube when a cube is randomly drawn from the bag. Okay, when all the possible outcomes of an experiment are equally likely, the probability of each outcome is 1 over the number of possible outcomes. Okay, so in this case there were 4 different. You had 4 different outcomes. You could have picked a blue, could have picked a red, could have picked a green, could have picked a yellow. Okay, you had 4 outcomes. Right, and that was our denominator. And each of those, since they were equal, there were 10 of each in there, equally likely, that would be 1 out of 4, 1/4, and that's the same as we achieved up top there. Okay. Now, an event is a collection of outcomes, and when the outcomes are equally likely, the theoretical probability of an event can be expressed as the number of favorable outcomes, very important word there, over the number of possible outcomes. So the truth is, what is supposed to happen? Okay, the theoretical probability measures that which is supposed to happen in a perfect world. Okay, in a perfect world, the probability of these would be 1 out of 4. Okay, 1 out of 4. Now, the theoretical probability of drawing a blue cube is, like we had mentioned before, 10 out of 40, because there are 10 blue cubes, 40 total cubes, 10 out of 40, which was 1/4 reduced. Okay. Okay, and is each color equally likely to be chosen? Okay, and that, and theoretically, yes, it is indeed. Each color is equally likely to be chosen. Will that happen? Probably not. Okay. So how do the theoretical probabilities of choosing each color from exercise 4 compare to the experimental probabilities you found in exercise 1? Well, the blues were perfect. Okay, the blues turned out to be, actually the blues weren't, I guess they were perfect. Yeah, because I picked how many times? I picked 20 times. Yeah, blues came up 1/4 of the time. That's right. Blues were perfect both times. Well, theoretically perfect. Red was 25%, or 1/4 the second trial, but yellows just blew us away. I mean, they were 1/2 of the chosen pieces in the first one, and then they were 7 out of 20, or 35% in the second trial. So not fantastic, but not incredibly far off, I guess. That's my answer. Okay, so now we have an experiment, flipping a nickel and a dime. All right, so the first step in finding theoretical probability of obtaining a heads on a nickel and a heads on a dime is to list the sample space. Okay, and here's a piece of vocabulary. I think we've talked about it before. For this experiment, the sample space is shown below. And you can see right there what the sample space is. It is actually all of the possibilities. Okay, all of the possibilities right there. Possibility of throwing the nickel. You throw a nickel then a dime. Okay, so you are doing 2 things. It's a little bit different than a single event probability. So you have a nickel heads, dime heads, nickel heads, dime tails, nickel tails, dime heads, tails, tails. Okay, so you have those. You have 4 4 distinct possibilities, and those 4, if the 4 counts are fair, these outcomes are equally likely. Okay, so the probability of each outcome is 1 over 4, or 1/4. Okay, and if we go down, the probability of 2 heads is also 1/4, or probability times 2 heads, and that equals 1/4, which seems almost like amazing. Wow, to do 2 heads in a row, how lucky is that? Okay, well, it's no more difficult than any other possibility. Okay, so in truth, it's not all that amazing. Alright, so now we're going to roll a cube here. Well, we're going to pretend we're rolling a cube. We're going to consider a chance experiment of rolling a number cube. Okay, so what I want you to do in this number cube, just to give you a little bit, is a regular number cube, 1 through 6. Okay, so I want you to go ahead and do these, A, B, and C. Alright, and come on back and we'll check in. Okay, let's see what you got here. Alright, so now first thing here is we want to come up with the sample space, and then list the probability of each outcome in the sample space. Okay, now the sample space this is a one event here. Okay, it's just doing one thing. Consider the chance experiment of rolling a number cube. Okay, so you're going to roll one number cube one time. Okay, and there's your sample space is 1, 2, 3, 4, 5, 6. Those are the 6 possible events, and each outcome has a probability of 1 over 6, or 1 out of 6, or 1/6. Okay, and you can see that pretty easily. All right, so the truth is that chances are the same for each number to come out, but the likelihood that that will happen is not as good if you the less times you do it. Okay, so here, what is the probability of rolling an odd number, okay, with this same number cube? And then all we have to do first, of course, is to find our sample space, and in this case, our sample space is 1, 3, and 5, okay, because they fit that criteria. They are all odd numbers. And that would be 3 out of 6. Okay, 3 out of 6 would be the probability of rolling an odd number. Now, what is the probability of rolling a number less than 5? Again, our sample space, 1, 2, 3, 4. Okay, therefore, 4 out of 6, or 2/3, and actually I fixed this one here. Rolling an odd number was 1 out of 2, actually. Okay, so there you go. This is probably pretty simple, but again, probably more important is getting used to the vocabulary, sample space, chance event, etc., etc. Okay, there we go. So we are going to consider an experiment of randomly selecting a letter from the word number. Okay, the word number. We did this before with the word probability, but in the word number, we do indeed have a sample space of number. Okay, we do have one possibility for each of those letters. Therefore, they all reside in our sample space. Okay, and then we're going to list the probability of each outcome in the sample space. Well, don't really need to do that. Each outcome has a probability of 1/6. Okay, because there are 6 numbers, and each of them has a 1/6 chance of being selected. Okay. What is the probability of selecting a vowel? This is very similar now to what we were doing with the coins. Our sample space now for vowels is actually just 2 of those, U and E, and that's 2 over 6, or 1/3 probability of selecting a vowel. What is the probability of selecting the letter Z? We haven't seen this in a while, and of course there is no Z in number, so therefore it is 0 over 6, or 0 probability. Okay. Now we're going to consider an experiment of randomly selecting a cube from a bag of 10 cubes. Okay, now we know there are 10 cubes. There they are, little little boxes there below. You are to, oopsie daisy, I just did this for you. Anyway, okay. So the task was to color the cubes below so that the probability of selecting a blue cube is 1/2 or 1/2. And you can see if there are 10 cubes, so 10 possibilities, your sample space is 10, and then we have 5 of those, because that is equal to 1/2. Okay, 5 out of 10. So therefore I'd have to color those blocks, 5 of those blocks, blue. Okay, so go ahead. Why don't you do B, and actually, yeah, do B first, and then we'll look at it together. So, yeah, do B and come on back. Yeah, there is indeed. Let's see what you got for this one here. Okay, this one might have been a little bit tricky. I don't know, maybe, but I ended up coloring in eight boxes blue, and I'll show you why. Okay, I looked here and I went back and harkened back to something we'd done a long time ago. I need to actually figure out what 4/5 of 10 is. Okay, 4/5 of 10, and if you remember our very friendly word of, okay, and of is going to tell us that we are multiplying. Therefore, if we multiply 4/5 times 10, or 10/1, again, fractions are so useful with this type of operation, and we get 40/5, and that 40/5 is equal to 8. And therefore, I was able to know that I needed to color in 8 of those boxes. Okay? All right. And here we go. Looks like one of our last problems here. Students are playing a game that requires spinning the 2 spinners shown below. Okay? A student wins the game if both spins land on red. Okay, so you're going to spin one and then spin the next. You win if you spin red on both. So, what is the probability of winning the game? Okay, remember to list the sample space and the probability of each outcome in that sample space. And they're giving us a hint or a heads up right here, telling us that there are 8 possible outcomes to this chance experiment. Now do remember though that this is a two spinners, so it's a 2 event probability. Alright, so we are going to spin one, spin the next. So when you develop or put together your sample space, and I would recommend a table, 2-column table with trial 1, trial 2, or spinner 1, spinner 2, and go from there. And if you want to, you can look back at a very similar problem was with the coins, flipping coins, heads and tails. So go ahead and put that together and give us a probability of winning the game, and come on back. All right, so here we go. My sample space right here, spin 1, spin 2, and hopefully you set it up the same way. If you didn't and you want to give it a whirl again at any moment, just go ahead and just pause and redo things if you need to. Now, my first, this is my winning. Go ahead and start with my winning round would be a red and red. Okay, so I can spin red on the first one, and then red again. Okay, and that would be one of the events, one of the outcomes in my sample space. Another outcome would be red and then blue. Red here, blue here. Okay, all right, and you can see where this is going probably. Next would be red and yellow. It's a very good way to actually to build your sample space. Is begin with one color in your first, and then go through each subsequent color on the second spinner. All right, and then of course red, green. All right, there we go. So every time we spin red first, we have 4 different possibilities because we have 4 on that second spinner. And you could probably see or begin to see a bit of a shortcut here in terms of how many of these possibilities there are. Okay, again, I'll just continue. Now I'm going to go with blue. Do everything with blue. Start with blue, blue, blue then red, blue then green, and then blue then yellow. Okay, and as you can see, we have 8 different possibilities. like we were already told. Okay, 1, 2, 3, 4, 5, 6, 7, 8. 8 different possibilities or 8 different outcomes in this sample space. And that's the only one that works, that first one right there, that first outcome. Red on the first spinner, red on the second spinner. And that's the way we win. Okay? So the probability, how do we build the probability of that? Well, you know, we have our one event that gives us the win out of 8 possibilities, and we get our probability of 1/8, or 1/8. As you can see, each one of these had the equal probability of 1/8, 1 out of 8 chance of occurring. Okay, there we go again. We are just at 30 minutes, 30 and change, maybe 31 minutes, and at our lesson summary. All right, when all the possible outcomes of an experiment are equally likely, the probability of each outcome is 1 over the number of possible outcomes. Okay, so when you have an equally likely experiment, you're always going to have a unit fraction that is going to represent that probability. Okay, a unit fraction, and that's a fraction with a 1 in the numerator. Okay. And an event is a collection of outcomes. Okay, that's an entire event, is the whole collection of all the outcomes. And when all the outcomes are equally likely, the theoretical probability of an event can be expressed as number of favorable outcomes over number of possible outcomes. And of course, theoretical is what should, in quotes, happen, what should indeed happen. Theoretical probability. So we talk about theoretical probability when we go into some endeavor, but what we do find, it's nothing you can really truly count on, but it is very, very necessary in some cases to have that theoretical probability to work with, because we can actually more closely estimate or predict events. Okay? Anyway, yeah, good luck with the problem set, and hopefully you're enjoying this probability module. I sure am. I'm enjoying the short videos, as I'm sure you are, and also just the building of a better understanding of how all of this works.